So using delta H in conjunction with Stoich is actually pretty easy. So here you can see the enthalpy change of the reaction. It's about negative 3,000. So that means heat energy is released. That's exactly what we would expect because what you see here is a combination with oxygen and then we have carbon dioxide and water. So this is a combustion reaction. So of course heat is going to be released. Those are always exothermic. You have to start with a balanced equation, and then this delta H of the reaction applies to that balanced equation. So approximately 3,000 kilojoules of energy are released when 2 moles of the ethane combine with 7 moles of the oxygen to give us 4 moles of the CO2 and 6 moles of water. If you don't have those exact mole ratios, then you have to adjust the delta H value proportionally. So we just do that through dimensional analysis, meaning we start out with 1.5 moles of the C2H6, the ethane. I always put it over 1. And then, you have to cancel out moles of the ethane because the question is asking how much heat would be released. So we know we want kilojoules up here. Okay, are we allowed to do that? Are we allowed to go from moles of one thing to kilojoules? You sure are when you have a delta H value for a balanced reaction. So the kilojoules, 3,120. Do not put 1 mole here because it's not for 1 mole. It's for every 2 moles of the ethane that are combusted. All right, the answer down here, negative 4,680 kilojoules. 2 quick things. Sig fig wise, it looks like our given, we only have 2 sig figs. So let's round that to 2. So 4,700, or you could use scientific notation. And then the last thing, it says how much heat would be released. So we're actually saying 4,700 kilojoules would be released. You really don't need the negative sign there. I'm not going to be super picky about it, but it would be redundant to say negative 4,700 kilojoules are released.